Hi everyone, I'm Cristina and together with Brian we are performing a recording today for you on the impact of different shimming strategies on water Linewidth at 14.1 Tesla. So this is a video which was requested by the ISMRM Educational Committee, the Molecular and Spectroscopy Chamber. So today we will be discussing a little bit what's shimming. We will be looking at a global study shim, which is a linear shim, and we will be evaluating the quality of this shim by looking at the water line within the hippocampus. Then, in the next video, we will be comparing this water line in the hippocampus with the mixed brain region in the cortex striatum and containing a little bit of CSF. Then, we will be looking at map shim, so we're performing a map shim using an ellipsoid covering the entire brain, and again we will be evaluating the water Linewidth as a quality of our shimming. Then, using again a map shim, this time we will be performing a shim on the voxel which is covering the VOI MRS, in our case the hippocampus, and again evaluating the quality of the shim looking at the water Linewidth. So what is shimming? So it's the experimental minimization of the B0 variations. Probably you all know that there is a consensus paper on B0 shimming, which is quite useful, so I recommend you reading it. Then why we are performing this shimming? Because any object introduced in a homogeneous magnetic field will distort this field according to its magnetic susceptibility. And we all know that an extra homogeneity of the B0 is essential for achieving high quality MRS data and also for a quantitative measurement of brain metabolites. How do we do this shimming? By a fine adjustment of the B0 homogeneity via field gradients produced by shim coils, which are contained within a shim system. So, what will be our starting points today? We will be first looking at an automated global study shim, which is performed each time at the beginning of each study. It's a non-localized adjustment of the linear shims X, Y, and Z using 3 iterations, and usually it's performed using starting with the starting value, which is called tune-up shim on our 14 Tesla, and today the tune-up shim values are all at 0. Map shim. What is map shim? It's a fast shimming procedure based on a previously measured 3D magnetic field distribution, which is also called a field map or a B0 map. First, we will be evaluating an ellipsoid, which is covering the entire brain or a specific VOI, the hippocampus in our case. So, starting points. We have a rat in our magnet. It's under isoflurane anesthesia. We will be looking at the hippocampus. So here you have an image with the hippocampus. The position of the rat in the magnet is tail prone, and we are using a home-built surface coil, transmit receive, and here it's a tuning and the matching showed of today. So let's go now to our live demo. So in the interest of time, we already did some acquisitions before. And what have we done before? So we first acquired a localizer to just see where the animal is positioned. For this localizer, we just did an MR scan with a basic frequency adjustment. Then we performed a second localizer that you can see here, where we, before acquiring, let me show it here for you, we adjusted the reference power. So because we are using surface coils as transmit and receive, we have to do a manual adjustment of the reference power. And in our case, we used a cornel orientation 2 millimeters, and very important, we use the gauge pulse as excitation. Why? Because they are known to be less sensitive to the B1 inhomogeneities. And when we are using surface coils, we all know that we have B1 inhomogeneities. So, this being done, the results are 0.024 watt in our case. Then, in this acquisition, in this localizer, we also performed, by using an automatic setup and an acquisition, we also performed the study shim. So please remember, the study shim was the shim, the non-localized first order shim on the entire head of the animal. Then we acquired a multi-slice localizer. So let me show it here to you. Why? Because when we will position the ellipsoid for the map shim, we would like to have a better view of how this ellipsoid is positioned. So this is a 2-minute acquisition just to have the 3 orientations. Then We perform the T2 turbo rear, as you can see here, to position the VOI in the hippocampus. We also perform the sagittal acquisition, the same sequence, different orientation, just to have a better view that the VOI in the hippocampus is well positioned. And then we acquired, you can see here, a STEAM sequence, and here it's our VOI in the hippocampus. Here, and let me show it to you here. Yeah, and in the reconstruction we can see that after the study shim, so the first order shim on the entire head, we have 58 Hertz. Then we acquired a T2 turbo rear, this time in the corner orientation. And why we acquired it? Because we wanted to perform the so specific map shim. So how did we do it? First, we acquired the B0 map. These are the parameters of our B0 map, and here is our B0 map, as you can see here. Then afterwards, we did this acquisition of the T2 turbo rear using, let me show it here, the map shim on an ellipsoid without iterative corrections, because it's an ellipsoid covering the entire brain. And as I told you, by using these three different orientation in this localizer multi-slice, we can very well position this ellipsoid. Very important, the ellipsoid should cover the full brain if you're looking for the full brain, and also you should pay attention that the ellipsoid, it's not, it's close but not touching the brain, the scalp, the bone, okay? Then, this acquisition being performed, let me look here. What we are doing usually is that we are saving our shim. So the ellipsoid, it's E13, I think, the acquisition. So we saved our shims, and then we performed again the same STEAM acquisition as before, and we are looking now at the waterline. So you can see the waterline width improved from 58 Hertz to 37 Hertz. So this is quite good. As you probably know, for single voxel spectroscopy or for spectroscopy in general, the waterlines, they should be as small as possible, as narrow as possible. However, this 37 Hertz is still not enough to perform accurate and reliable single voxel spectroscopy. So what we are doing now, in the next acquisition, this is again the same STEAM sequence with the voxel positioned in the same place. This time, if we look here in the shims, we will be performing a map shim again using the same B0 map that we acquired before, and this time we selected the automatic shim volume, meaning that it's for shimming for the map shim, we'll take the hippocampus VOI that we selected before, and we are adding 0.5 millimeter as margins, and this time we are performing an iterative corrections. So each time when we use VOIs which are a small size, we are adding these margins. However, if you use a big VOI which is covering the entire brain, margins maybe they are not needed. So let's just continue and see what is the quality of our waterline in this case. So you can see here the scan shim, so the map shim is performed now. It takes a little bit of time. Okay, the reference scan adjustment. So you can see here that there is a first estimation of the waterline with 13.7 Hertz. So we are on the good way. Let's putting it like this. So maybe just some details about the sequence while the adjustments are done. So this is a voxel size 2.8 by 2 by 2 millimeters. This is the position. You can see it here in light green. In dark green, it's the VOI for the map shim with the 0.5 millimeters of margins added to this voxel size. We have an echo time of 3 milliseconds, a mixing time of 10 milliseconds, and 4 seconds repetition time. 8 averages, maybe it's a bit a lot, but yeah. And then of course the stem, the 3 90-degree RF pulses of the stem. And of course we have here in preparation, you can see that we have no water suppression. We slightly adjusted our VOIs, our OVS, sorry, and here you have especially the spoiler strength was modified, and also the duration of the pulse was modified from. Here are the details. So, and also the slice thickness, sorry, was slightly increased. So these are adjustments that you always have to perform when you decide the rain region and the voxel size that you would like to measure. So we are almost done, 8 seconds now. Okay. So if you look at the reconstruction, we are at 14.7 Hz. This is an excellent quality of shimming for performing single voxel spectroscopy. So now we can load this in top spin just to double check that everything is okay. Process, adjust the phase. We save and we do the command line peak width. And we can see that we are at 14.3 Hz. And very fast, a short demo about, so as you can see here, I'm selecting my application MRS single voxel spectroscopy. So in our group, we created applications, so a folder, different application folders with different names based on the application that we are running. So in this case, it's MRS single voxel spectroscopy. We are in the hippocampus, and you can see every sequence that we will be running. It's created, it's saved properly, and you have a number for each of them, which indicates the first one, second one, third sequence that has to be run. That's quite important because, because why? Because it helps you to go faster in your experiment. So this is our sequence, as you've seen. So now if I'm clicking on the vapor water suppression, and if I go in sequence, setup, shim, and I just use the current shims, and in routine I'm putting 16 averages, maybe 16. Let's see what we get with 16 averages, and we continue. We will get the water signal, the metabolite signal. So just by curiosity to see how the water suppression is performed and how good the spectra are looking. So again, we are adjusting reference scan, and while this is acquired, just a small hint about the water suppression. So the water suppression is shown here. We have a vapor water suppression. We have 350 Hz. For the bandwidth, this has to be adapted based on the magnetic field that we are using. We have the RF pulses hermits. It's something that we've modified because of the surface coil. In our case, that we changed the flip angles. As you probably know, vapor, it does not contain 90 and 180 degree flip angles. It contains two sets of RF pulses, and with a difference in flip angle of 1.70 Hz. 1.78. So this difference in this factor between the two flip angles has to be respected. And in our case, this was the best agreement and the best way to acquire the most reliable water suppression. The only thing that we are changing, it's the duration of the last delay between the RF pulses for vapor. In our case, the best one was 26 milliseconds. We are not going to the minimum one. And let's see, receiver gain, adjustment. And as you can see already at the first hint, You can see that you have nothing inside in your spectrum shown in this window. It means that the water suppression is quite good. So let's see the scanning now. We only have 16 averages with a very small voxel, so probably the quality will not be amazing, but ISMRM requested a very short video, and yeah, just to enter in this 10 minutes of video recording, I've decided to make a very short metabolite acquisition. Let's go here and then load the acquisition in top spin to see the quality of a spectrum, metabolite spectrum. Yes, load in top spin. So this is the quality of our spectrum. As you can see, this is a water residual. It's at the same height like N-acetyl aspartate, and these are the metabolites: N-acetyl aspartate, total creatine, total choline, taurine, and so on. The quality is quite nice. The shimming worked very well, and yeah, I hope that you appreciated this video. And before finishing, I would just like to explain you the next steps. So the video will be added online on our group website, but also ISMRM will be adding this video on their website. For the next video, would like to go to a mixed brain region and just to see what is the difference in shimming between a pure hippocampus brain region and another brain region containing different other brain regions. Then would like to do a demo on water suppression and how to acquire a good quality brain metabolite spectrum. And if you have questions, please just write us an email. Cristina and Brayan, yeah, our emails are here. Then I would just like to remind you that we started together with Jamie Neer, he's here. We started an initiative which is called Towards Standardized Preclinical MRS, a multi-center study. So our initiative was presented during the MRS study group virtual meeting on the 18th of January. The video is online on the ISMRM website, also on our website. And if you would like to participate, just write us an email. And then just finishing, I would like to thank you for your attention. I would like to thank ISMRM for inviting us. And I would very much like to thank all my students and my colleagues from the MRS for Brain group. Thank you very much, and thank you, Brayan, for being here.